Hello everyone, welcome to the modern networking lecture series. This is lecture number 7. So today we will see some topics related to routing, and then we will just give a basic definition of SDN and NFV, the main topics of this lecture series. So routing, just an introduction, what is the meaning of routing? Okay. So in any network we have various nodes. Okay, router is one of the nodes. So the primary we can say the function of the internet is to accept the packets from the source station and to deliver them to the destination station. So when any of the node, when any of the host, it passes a packet, the data in a form of a packet. So before reaching the destination, it may pass through various nodes. Okay, that node may be any it can be a router. So the basic function is to deliver that particular packet from source to destination passing through various nodes. Now to deliver the packet along the network, a route must be determined. So what route the packet should go so that it can reach the final destination. So this thing is achieved through a function called as the routing function. Okay, so the routing function ensures that that packet reaches from the source to the final destination. So the selection of a route is generally based on some performance criteria. So we have some criteria based on which the route is selected. Now the simplest criteria can be the minimum hop. Okay, so we'll see this with an example in the next next slide. So this is the example. So this consider these are some nodes. We have N1, N2, N3 and so on. We have 6 nodes. Okay, and you can see the numbers between the nodes. Okay, so this is actually the cost. Okay, so cost can be anything like minimum number of delays, or the cost can be any factor. Okay, so here from when a packet goes from N1 to N2, the cost is 2. From N2 to N3, the cost is 3. Okay, and the hopping means what? Suppose we want to send a packet from N1 to N3 from here to here. Okay, so if it goes through this path, okay, so this is the first hop and this is the second hop. So with two hoppings, it reaches N3. Okay, and if it wants to reach N6 through this particular path, okay, it will go with 3 hoppings. So this is the number of hops. So one of the criteria is how many number of hoppings are required. Okay, so suppose if you want to reach from N1 to N6, if we are considering the less number of hops, then maybe this can be one of the path that 4 hoppings. Maybe some other path number of hoppings may increase. So the router will send in such a way, the direct in such a way that minimum number of hops are involved. Another criteria, it can be like it can be least cost, least path. Okay, least cost path can be another criteria. Okay, like suppose if we want to send the packet from N1, okay, to let us say N6. Okay, you want to send the packet from N1 to N6. Okay, so the minimum number of hop will be from here to N3 and N3 to N6. So here we see there are only 2 hops. Okay, there are only 2 hops. But if we consider the cost, okay, I'll just draw with another pen. So if we go from N1 to N2, then N2 to N3 and N3 to N6 in this way, so the total cost is 5 plus 3, okay, it is 8, and 8 plus 2, okay, it is 10. Okay, while here the number of hops are increasing from N1 to N2, 1 hop, 2 hop, 3 hop, so there are 3 hops. Okay, but the cost is less. Okay, but from N1 to N3 and then N6, the hops are less but the cost is more. Okay, so it may depend what type of route is selected. Okay, as we can see from here also. Okay, so least cost path is generally preferred. Now how do we know this particular, how does this node knows that about other nodes? Okay, because this N1 is directly connected to N2 and N4, but it doesn't know any information about N3 and all the other nodes. Okay, so we have a set of routing protocols. Okay, so using the routing protocols, the router knows about the other routes other networks, other nodes which are there in the network. Okay, so the routers in a network are responsible for receiving and forwarding packets. Okay, this is their responsibility, that they receive and they forward the packets, okay, through the interconnected networks. Each router makes a routing decisions based on the knowledge or topology and traffic delay conditions of the internet. So the router has to make some decisions where to send the packet so that it reaches the final destination. So to make such dynamic routing decisions, we have a set of routing protocols. Okay, now we can classify the routing protocols into two types, which is based on the autonomous system, based on the autonomous system concept, based on the concept of autonomous system. Now what is the meaning of an autonomous system? Autonomous system can be a set of networking nodes which are owned by a particular organization or in a particular geographical area. Okay, so that are the routers. Okay, so we'll see by the example afterwards. So there are two categories of routing protocol. One is the interior routing protocol, the other is the exterior routing protocol. Okay, so in this diagram we can see there are two autonomous systems. Okay, one is this one. Okay, this is one of the autonomous system. This is another autonomous system. So this router, okay, let us assume this R4 of this autonomous system. So R4 of this router, it will exchange its information with R1, then R4 will exchange its information with R3, and so on. So every router in this particular autonomous system will share its network information with the other routers. So they need a protocol. So that protocol is actually called as the interior routing protocol. Okay, so we can get the definition of interior routing in this case, that the routing protocol which is used inside the autonomous system by the routers to find the network information, that protocol is called as interior routing protocol. Then OSPF, open shortest path first, one is one of the interior routing protocol. Then similarly for this also we have some interior routing protocol, that is maybe OSPF, by which each router shares information with all the other routers inside that autonomous system and gets the information of the entire network. Then there is a router at the edge of this particular autonomous system. Okay, it shares the information of the entire autonomous system with another router which is in another autonomous system. Now for that purpose, the protocol which we use is called as exterior routing protocol. Okay, so by using exterior routing protocol, one of the router, it shares the information about the entire autonomous system with the other autonomous system router. Okay, so they will share this. You can see this pink line. So there is a green line and there is a pink line. So this green line, it represents the protocol, it is interior routing protocol. Okay, and this pink line, it shows the exterior routing protocol. So BGP, border gateway protocol, is one of the exterior routing protocol. Now these are some of the elements of the routers. Okay, each router, it has a interface. So you can see this is one of the interface, there's another interface, there's another interface. So there are various interfaces, and at each interface we have some buffers. Okay, the buffers, they may store packet which is coming in and one which is going out. Okay, so every router will have this at each interface, it will have a buffer. Okay, then it will also have forwarding table. From this particular, how this table is created, this table is created by using that routing protocols. So from this forwarding table, the router will know where to forward the table. Then there is a routing control and there is some routing policies. Okay, so this routing tables, they are created based on the routing control and the routing policies. Okay, now after this routers and routing information, we have something called as congestion control. Okay, now in like if in this case, suppose we have a router. Now this router is connected to multiple networks, many networks it can be connected. One of the networks can connect to the other router and so on. So if the traffic gets increased in this particular area, in this particular buffer, more and more packets are getting into this particular router, into this particular buffer, and the capacity in this buffer is overloaded now. Okay, this buffer is full. Now if this becomes full, then it is natural that all the other packets which are now into this router, they will get slowed down. Okay, so congestion can occur. Okay, so we have a congestion control mechanism, okay, by which the congestion can be reduced. Okay, so there are several congestion control mechanisms. Okay, so we can divide it into two broad categories. One is open loop congestion control, which is called as prevention. Okay, this mechanism is used before congestion occurs, and then we have closed loop congestion control, which is removal. This is used when the congestion has already occurred. Now these are some of the techniques, mechanisms with respect to open loop congestion control. We have this retransmission policy, window policy, acknowledgement policy, discarding policy, admission policies. So these are some of the policies which are used for open loop congestion control, and these are the policies which are used with respect to closed loop congestion control. This back pressure, choke packet, implicit signaling and explicit signaling. Okay, now we come to the main topic. Okay, now until now what we have done was just ground preparation for understanding why do we need this SDN and NFV. Okay, now we just a brief introduction about SDN and NFV in this particular session. So to provide adaptability and scalability due to ever increasing volume and the variety of network traffic generated by high demand sources such as big data, as we have seen in the previous lectures, that whatever the things we have now, that is big data, cloud computing, mobile traffic, they generate tremendous amount of data. Okay, and the data is unpredictable. So with the rapid increasing of such things, we need some we need to change some infrastructure. Okay, so for that purpose we deploy this techniques, that is software defined networking, SDN, and network function virtualization, NFV. So what is software defined networking? Now SDN, as we call it, is replacing the traditional networking model. So SDN provide an enhanced level of flexibility and customizability to meet the needs of newer networking in the IT trends such as cloud, mobility, social network, and the video. So this is the, you can say, the block diagram. Okay, so in case of SDN, we have, you can see we have two planes. One is the control plane, other is the data plane. At the data plane we have this devices, networking devices, the nodes. Okay, and at the control we have the controllers. Okay, so which give the which passes the commands to this particular nodes. Okay, so in SDN we divide the network, we divide this particular thing into two planes, that is the data plane and the control plane. In traditional networking, these two are combined in the single device, okay, but here they are separated. Now the functionality, as we have seen, so in case of SDN, there are two elements. One is the control function, other is the data function. So control function, it decides the route the traffic takes and the relative priority of the traffic. So all the decisions, they are made at the control plane, and data plane, it just forwards the data based on the whatever the control functional policy is made at the control plane. Okay, now SDN functionality. So before SDN, the control and the data functions were performed in the integrated fashion. Okay, that were whatever the router, bridge and packet, they used to perform both the decisions, control and data functions. Okay, so control in traditional networking is exercised by means of routing and control network protocol, which is implemented at each network node. Okay, now this approach is relatively inflexible. The traditional networking is inflexible and requires all network nodes to implement the same protocols. Okay, so same protocols must be used at each node. But with SDN, we have a centralized controller. Okay, and this centralized control, it performs all the complex functionality such as routing, naming, policy declaration and security checks. So this is done by the central controller. Next we will study, of course, SDN in more detail in the coming sessions. Next is the network function virtualization. So this NFV, it decouples the network functions such as routing, firewalling, IDS, this intrusion detection systems, then network address translation from the proprietary hardware and implement them as a software function. So all these functions, they are implemented in software part. Okay, so it utilizes the standard virtualization technique and that runs on high performance hardware to virtualize network functions. So all the functions, they are performed using the software commands. Okay, the concept virtualization is used here. So it is applicable, of course, both to wired and wireless network structures. Now NFV has a number of features in common with SDN, and they share these common objectives. The first is move functionality to software. Okay, now if we move the functionality to software, then we are not tied up to the property, the hardwares. Okay, we can use the hardware from any manufacturer and use commodity hardware platform instead of proprietary platforms. Okay, then use standardized or open application programming interfaces, APIs. Then support more efficient evaluation, deployment and repositioning of the network function. So these are the features which are common between NFV and SDN. So that's all for this particular session. We will continue now with this SDN and NFV in our coming sessions. Thanks for watching.